Okay, so today we're looking at connected particles. I'm going to snap over to the slides. So with connected particles, previously we've been looking at just single particles and how the forces work on those particles. But when we've got connected particles, we can think of them as one particle as well. So when we have kind of multiple things connected together, as long as they're all traveling with the same acceleration, these can be considered as one particle. So I'm going to put this slide back up actually just for a second in case you want to write this down. I'm going to talk through it as well. So this is the first question. Two particles, P and Q, of masses 5 kilograms and 3 kilograms respectively, are connected by a light inextensible string. Particle P is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. Particle P experiences a frictional force of 10 newtons and particle Q experiences a frictional force of 6 newtons. Find the acceleration of the particles and find the tension in the string and explain how modelling assumptions that the string is light and inextensible have been used. So, first thing we need to do with any of these is to make sure that we draw a decent diagram. So we've got here two particles, P and Q, both connected, both being pulled by 40 newtons. So let's draw these first of all. So I'm going to draw these just as a particle. You can draw them as a square if you want. So this is particle P. So particle Q and particle P, and these are connected by a string. So it tells you here that particle Q has a mass of 3 kilograms. So we're going to put our force going down here, which is 3g. Remember, 3g means 3 times by gravity, so mass times acceleration. We've then got here P, which is equal to 5 kilograms, so that's going to be 5g there, acting down. We are going to have two reaction forces acting up here. So we've got two reaction forces. Now, the thing to think about here is what's actually pulling each of these. So P is being pulled, or both of them are being pulled by a force which is 40 newtons. Okay, now P is being pulled by 40 newtons. However, it's being slowed down here by Q, but it's not Q that's slowing it down. The thing that's slowing it down is this tension which is in this string, and that's important to think about. Now, what's actually pulling Q? Now, you could say that it's the 40 newtons, but it's not the 40 newtons over here which is pulling Q. The thing which is pulling Q is this tension here again. So this tension. Now, the thing to notice that I've called this T and T, and that's because this is a light inextensible string, so I always mess that up. A light inextensible string, which means the tension in both of these is exactly the same. It means that the string isn't elastic, so it's not stretching. It's kind of a one fixed string that doesn't stretch, and it means that the tension across all of this is exactly the same. Now, we are missing a couple of things here. It also tells me that there is a constant frictional force on Q, which is 6 newtons. So let's put that in. So 6 newtons going back here, like so. And we also have a frictional force on P, which is equal to 10 newtons. So let's put that in there, like so. Now, this here looks pretty complicated, and it is complicated, but this is the starting point. This is the thing that you must have done properly, because if you don't get this right in the first instance, then you're going to mess all of this up. Okay, so let's just talk through it. We've got two particles which are connected by a string. Okay, we've got the first one is equal to so P is a mass of 5 kilograms. So the force acting down is 5g. Remember, the g is 9.8. Acceleration due to gravity. We've got this one over here, which is equal to 3 times acceleration times by g. I have forgot to put on here the reaction force. Now these reaction forces are going to be different, so let's call them R1 and R2. Okay, and that's that diagram drawn first of all. That's the important part. Okay, so let's just check that's all right. So there's our diagram drawn. One thing I have forgotten that is the fact that they are both accelerating. Now, because these are connected, they are accelerating at the same rate, so we can just put 1a on top of there, like so. So the first thing says, find the acceleration of the particles. So let's put a on here. So find the acceleration of both of these particles. Now, as I just said, both of these particles are moving with the same acceleration because they are connected and because that string can't stretch. So it's being pulled by 40 newtons. It's got a frictional force of 10 newtons for P, a frictional force of 6 newtons for Q, which does make sense actually because this is 3. So this has got a mass of 3, so the weight of this is equal to 3g. The weight of this one is equal to 5g, but obviously not necessarily because there could be a higher coefficient of friction for mu for each of these, but we'll talk about that later. The thing we need to think about is using the formula F equals ma, which I know we've already looked at. So all of these forces are equal to the total mass times by the acceleration of both of them. Okay, now that's really important, all of these forces together. Now remember I said to you to label the direction in which you're going with this, and we're going to go the direction which the acceleration is. So we're going to use R. So the resultant forces of all of these is going to be R, and that's going to be going this way. Okay, so we're now going to say that F equals ma, so I probably should have left a little bit more room here. So we've taken R as right, so this is our positive direction. So the things which are acting right in the positive direction are the 40 newtons force minus this 10 newtons force, which is the friction on P, the frictional force on P, minus this 6 newtons here, minus the 6 there. And that's equal to your mass. Now we're taking this mass as a whole. We're saying these are connected and they're traveling at the same acceleration. So this mass is going to be equal to 8 times by the acceleration, which is equal to a. So what we're doing is we're taking this as a whole thing. We're thinking about it as one whole thing. Okay. So the first thing we need to do then is simplify this side. So 40 minus 10 minus 6. 40 minus 10 minus 6 is equal to 24. So we have 24 is equal to 8 times by a. So the mass times acceleration of this one. Total forces, mass acceleration. And then we're going to divide that. So 24 divided by a, which is equal to 3 is equal to a. So a is equal to 3 meters per second squared, like so. So that's the first part of this done. So now I can say that on my diagram here, I know that the total acceleration is equal to 3 meters per second squared. So the next thing I need to think about here is part B. So that's part A done. So part B says, I'm going to put this back up just so you can see this. Find the tension in the string. Okay. Now it's worth noting at this point that there are 2 ways to find this tension in the string. And what we have to do is we have to single out one of these particles. So in that first part, we took all of these particles as one thing. But now what we need to do is we need to think about one particle individually. So whether that's this one or whether that's this one, you will get the same answer. Remember, these 2 tensions here are exactly the same. The tension pulling this forward is exactly the same as the tension which is holding this back. And it might even be worth showing you that you get exactly the same for this. So let's have a look now at B. I'm going to fold this up a little bit just so you can keep the diagram. So part B. So with part B, I am going to take the... Sorry, with part B, I am going to take Q. Oh, in fact, I'll do both. I'm going to take Q as the particle, which I'm going to focus on. And again, I'm going to take it going this way as positive. So we write down F equals ma, same as always, F equals ma. So what are the forces that are acting on Q? Now, basically, what we're doing is we're covering this up, okay? If I cover this up here, we're just looking at what are these forces which are pulling Q. So the forces which are pulling Q are the tension, which is acting right, like so, minus the frictional force on this, which is 6, which is equal to your mass. Now, it's just the mass of Q, which is 3, times by the acceleration, which I've also just worked out is 3 as well. Okay, so remember that this is for the particle Q, and here we're resolving the force going right. So forces, the tension acting right, minus the frictional force acting this way is equal to the mass of this particle, which is 3, times by the acceleration, which we know was just worked out as 3. So we're going to end up here with 3 times 3, which is 9, plus the 6, which is equal to 15 newtons. So 15 newtons pulling it that way. Now, I said to you, it doesn't matter which particle you can use on this. I'm just going to prove that. You don't need to do this. Okay, you only need to do it for one, but I will prove that it works for both as well. So again, we're using F equals ma. And this time I'm just going to take P. Okay, I'm just going to think about this one. So here for P, let's write down P, and I'm resolving with my forces going right. What are the forces which are acting on P here? Well, the positive force, which is pulling it, is that 40 newtons, minus the tension, which is holding it back, also minus this frictional force, which is holding it back, which is equal to the mass of this, which in this case is equal to 5, times by the acceleration, which is equal to 3. So we've got things a little bit different here because we've got more forces. We've got the 40 acting right, we've got the tension acting left, and we've got the tension in the frictional force acting left as well. So here, what we need to do now is we need to solve this. So we want to find T, so let's take T over, bring that 15 back. So I end up with 40 minus 10 minus 15 is equal to T. So 40 minus 10 minus 15 is equal to 40. We already know what this is. Minus 10 minus 15 is equal to the tension, which is exactly the same as when we did it for Q, which is the 15 newtons there. Brilliant. So we know that we've done that right. So this last little part here says, explain how the modeling assumption that the string is light and extensible have been used. So inextensible means that the acceleration of this object is the same throughout all of it. Okay, so this basically means the string isn't stretching. And because the string doesn't stretch, it means that when this particle moves, the other particle moves at exactly the same rate. Okay, the fact that it's light means that the tension's the same throughout the length of the string, and that the mass of the string is, we don't think about that. So we're not considering the fact that it's light. The word light means that you do not think about the weight or the mass of the string. And the fact that the tension is the same throughout, again, so this tension here, which we worked out, is exactly the same as this tension here. So let's just have a little check of that. Ooh, let's have a look, sorry. So yeah, the acceleration of the object is the same, tension is the same throughout the length of the string, and the mass of the string is negligible. And we've got the tension here, which was 15, which we've just worked out. So that's that question done. First one from the book done. Okay. So let's move on now. Now, these are the questions that most people, when they're doing this, tend to struggle because actually there's quite a lot going on. So Newton's third law is that every action has an equal and opposite reaction. We spoke about this when we were pushing on that wall, and I was saying, why am I not, as I'm pushing through the table here, why am I not falling through the table? And the reason that I'm not falling through the table is because the table's pushing back up on me, and that's the reason. So, therefore, when two bodies are in contact, if body A exerts a force on body B, then body B exerts a force on body A that is an equal magnitude and acts in the opposite direction. Exactly what I'm talking about. So why, as I'm pushing down on here, am I not falling through this piece of paper? The reason is, and it may sound weird, but the paper's pushing back up on me. So, let's get this let's get this big so you can see this and copy it down. So let's have a look at this textbook exercise. A light scale pan is attached to a vertical light inextensible string. The scale pan carries two masses, A and B. The mass of A is 400 grams and the mass of B is 600 grams. First of all, first thing I'm thinking about that is the fact that it's using grams. So be really careful with that, because actually we need things in kilograms. And I've seen lots of mistakes with that. So A rests on top of B, as shown in the diagram. So there is a diagram there for you to see. And the pan scale is raised vertically using a string with an acceleration of 0.5 meters per second. Find the tension in the string. Find the force exerted on the mass B by A, mass A, and find the force exerted on mass B by the scale pan. So, first of all, exactly the same as always. First thing we need to do with this is make sure that we are drawing out a very strong diagram. Now, you've already got a diagram in this, so let's just use the model as well. So we've got this. This is going to be the scale pan. Sometimes they say it's a lift, and they use the lift example. They say that A is in top on B, and B is on the pan scale. Scale pan, sorry. So we've got B on the bottom here, which is 0.6. And then we've got, this is B. And then we've got A on top of that, which is equal to 0.4. There, like so. So we've got the tension which is pulling this up. This is going to be the tension in the string pulling this up. There are going to be forces which are acting down here, which are going to be pulling it down, and that's going to be from both of these. Notice that in this question it says a light scale pan. That means there is no mass on this. Now obviously there would be, but in this case they're just considering that there's no mass on here. So the first part says, find the tension in the string. So what we're doing here is we're finding the tension here in the string by considering all of these together, considering this as one whole particle. So the things which are acting down on this, there's actually two things which are acting down. I'm going to do them like this. Notice that's coming from A. So there's two things which are acting down. The first one is equal to this part here, which is going to be equal to this 0.6 G. The next one is going to be this 0.4 G acting down as well. So this is the weight acting down of B and the weight acting down of A. Now you could, if you wanted to, because we're thinking about these as a whole, write this as 1G acting down. Well, I've just decided to write them write them both separately there. So the next thing we need to consider is using the F equals ma. Force is equal to mass times by acceleration. So we know, sorry, there's something else that I've missed on here. We know that the acceleration is acting, pulling it up. And that acceleration is 0.5 meters per second squared. Okay, so that acceleration is acting up. So let's start thinking about this now. So what are the forces which are acting on this? So the forces which are acting on this are the thing which is pulling it up. Now I'm going to resolve this, resolve all of it going up. Okay, so the forces which are acting on this, well, what is pulling this up? What is pulling this scale pan up. Well, the thing which is pulling it up is the tension in this string. So it's equal to the tension on here minus the forces which are pulling it down. So that's going to be the 0.4 G minus the 0.6 G, which is equal to the mass of all of these. So that's the mass of A, the mass of B, and the mass of the scale pan. Now, there is no mass of the scale pan, so it's just going to be equal to the mass, which of both of these, which is going to be the 0.4 and 0.6, which is 1, times by the acceleration, which is acting up, which is equal to 0.5, like so. So let's start trying to solve this. So we've got T minus 1G is equal to 1 times 0.5, which is equal to 0.5. So now let's take all of this over. So T is equal to 0.5 plus 1 times by 9.8. 0.5 plus 1 times by 9.8 is equal to 10.3. Remember that we are doing all of this to 3 significant figures, or 2 significant figures, it does sound different, but we'll do it to 3, which is 10.3 newtons. So that means there's 10.3 newtons, which is pulling this up. 10.3 newtons is pulling this up. That's what this tension is. Okay? So the next part, part B, says, find the force exerted on mass B by mass A. Okay? Now the force which is being exerted on mass B is this reaction force here, which is happening on B. So what is stopping A from falling through B? And the reason it's not going through B is because B is pushing back up. So as A is pulling down, B is holding it up, and it's the reaction force that we're looking for here. We're looking for the reaction force on A. That's the thing that's pushing A up. It's not the tension. The tension is pulling all of this up. But the thing which is actually pulling A up is that reaction force. It's the force from B which is pushing this up. That can be quite difficult to think about. So, what we are thinking about here, let's draw a little diagram. So our diagram, we're going to be thinking about A, like so. We know that the mass of A is equal to 0.4 kilograms. Remember, I've converted that. We've got our reaction force, which is acting up. Now that reaction force is from B. And then we've got our weight, which is equal to 0.4 G acting down. We've still got that acceleration. Okay, the acceleration which is pulling up is equal to 0.5 meters per second squared, like so. Now, just to make it really clear, it's this reaction force, which is the force which is being exerted by B. Let's just check what it said. The force exerted on B by mass A. So the force which is exerted on B by mass A is that reaction force, which is the same as the force which is exerted by B pushing it up. So the force which is acting down on from A is the same as the force which is acting up from B. So with this one here, we've got a nice little diagram. So we're just going to resolve this. So let's F equals ma, mass times by acceleration. So what forces are acting on this? Well, again, let's just going to say I'm going to resolve this up vertically, take it up as positive. The forces which are acting on this are the reaction force which is pushing this up, minus the weight of this, which is equal to 0.4 G, which is equal to the mass of this, which is equal to 0.4, times by the acceleration, which is equal to 0.5. So let's just solve this, take it over, times by that 0.4 G. So 0.4 times by 0.5 plus 0.4 times by 9.8, which is equal to 4.12. So the reaction force of this is equal to 4.12 newtons pulling it up. So let's have a little look at this. it might also be worth mentioning here that this reaction force, it's asking for, the force which is exerted on mass B by mass A. Now, the force which is being exerted on mass B by mass A is exactly the same as the force which is pushing A up, this reaction force. That's kind of the thing that people struggle with here. So, let's have a quick look. 4.1, they've rounded to two significant figures. Yeah, absolutely spot on. So the last little part is C. So part C. Now part C says, find the force exerted on mass B by the scale pan. Now this one here, because this is a light scale pan, there's no weight to this scale pan. Now, usually, if you're in a lift or if you're in something, if you've got a scale pan, there would be some weight on this. Now, because there is no weight on this, what we're actually going to find is that the force which is being exerted on A and B, or sorry, on B, well, it's on A and B because it's going through both of them, is exactly the same as this tension, because there is no mass of this lift. It's not the tension doesn't have to pull up the weight of the scale pan plus the weight of B plus the weight of A. It's just pulling up the weight of A and B. And the reason it's just pulling up the weight of A and B is because there's no mass of the scale pan. So it's just literally pulling up these two. So these two here are going to be the same. So what we've got here is we know that the reaction force of the scale pan is going to be exactly the same as the tension, but I can prove that to you if you want. It's going to be exactly the same process. So if I think about these two here, like so, you've got 0.6, you've got 0.4, you've got the acceleration which is acting up, which is equal to 0.5 meters per second squared. We've got, this is our scale pan. We're trying to find this reaction force here, okay? The reaction force on mass B by the scale pan. So it's going to be equal to 0.6 G acting down plus this one here, which is equal to 0.4 G acting down. Both of these are acting down in this diagram. It's not just this top one. And then the we're going to resolve, use F equals, oops, sorry, lost me a little bit there. So use F equals MA. The forces which are on this are the reaction force, which is the one we're trying to find, minus 0.6 G minus 0.4 G is equal to the mass of both of these, which is equal to 1 times by the acceleration, which is equal to 0.5. Notice this is exactly the same as this formula up here. It's just we've got T and R, which are different. Probably should have said we're resolving going upwards. So with this one here, it's exactly the same, and the reason that it's exactly the same is because the scale pan is light, so there's no weight to that. Now, there are going to be questions where we don't have that, where we do have a lift. There's the weight of a lift or the weight of the scale pan. But in this case, we can solve this. It's going to be exactly the same. So R is equal to 10.3 newtons there, like that, which is exactly the same as the tension, what I said before. So let's have a look now at the next question. I'll transition that for you so you can have a read of that. Might try and zoom in a little bit. Can you see that a little bit better? No? Okay, so a woman travels in a lift. The mass of the woman is 50 kilograms. The mass of the lift is equal to, so we're looking at one with the mass of a lift now, is equal to 950 kilograms. The lift is being raised vertically, similar to the last one, by a vertical cable which is attached to the top of the lift. The lift is moving upwards with a constant deceleration. So that means it's slowing down, actually. That's really important. We haven't looked at that yet, of 2 meters per second. By modelling the cable as light and inextensible, find the tension in the cable and the magnitude of the force exerted on the woman by the floor of the lift. Now, this is exactly what I was just talking about. So, with this one here, let's first of all draw a really good diagram. So we've got here a lift, like so. Excuse the squeaky pen. We've got the tension in this lift, which is pulling it up. Okay? We've got the mass of the lift, which in this case is equal to 950 kilograms. Just check. Yes, so 950 G acting down. We have the woman in here. Let's draw a woman. There she is. And she has a weight of 50 kilograms. So I've also got 50 G acting down. Now, the important part of this, it is travelling vertically, so it is travelling upwards. So I need my acceleration there, like that. However, it's travelling upwards with a constant deceleration, okay? Which means that this is slowing down. So I've got to say this is negative 2 meters per second squared. Minus 2 meters per second squared. And that diagram's enough there. We've got our woman, who's 50 kilograms. We've got the mass of our lift in this case, which is the 950. It's not light this time. So the first thing says find the tension in the cable. This is 3 marks. This is from the old M1 paper, it's 2013. So let's have a little look at this. Part A. So first of all, because we're finding the tension in the cable, we're resolving this as a whole. So we're going to take, we're going to resolve this vertically, like so. We're taking all of these things into consideration, okay? So we're going to be using, same as always, F equals ma. Force is equal to mass times by acceleration. So what forces are acting on all of this? So the forces which are acting on all of this, what's pulling it up? The thing which is pulling it up is this tension here. So that's acting up. What's pulling it down? What's holding it down? Well, minus 950G minus the 50G as well is equal to the mass, which is the mass of all of these together, which is going to be 1,000 times by the acceleration, which in this case is equal to minus 2. So let's solve this now. So we've got, let's take all of this over first of all. So T is equal to 1,000 times by minus 2 plus 950G plus 50G. Let's do all of those things. 1,000 times by minus 2 plus 950 times by 9.8 plus 50 times by 9.8, which is equal to, my tension is equal to 7,800 newtons. So the force which is pulling this up is 7,800 newtons there. So next up, let's have a look at B now. The force, the magnitude of the force which is exerted by the woman, on the woman by the floor of the lift. So with this one here, part B, now this is where it's a little bit different, because all we're thinking about here is this woman. Now what's the reaction force on this, which is pushing up on the woman from the lift? That's what we're looking for here. So we know that there's a force acting down on this, which is equal to 50G. We know that what is pulling this woman up? So the thing that is kind of pulling this woman or pushing the woman isn't the tension. I mean, it is kind of overall, if we're taking this as a whole. Well, what's the thing that's actually pushing the woman up? Well, the thing that's actually pushing up the woman up is the floor of the lift. It's the reaction force. It's the reaction force which is pushing this woman up. So this is what we're trying to resolve now. So we're going to resolve this again vertically, like so. So it's the reaction force R. I should say F equals ma. We know force is equal to mass times acceleration. So what forces are acting on this? The force which is acting up is R, minus the force which is acting down, which is 50g, is equal to the mass of the woman, which is equal to 50 times by minus 2. Nearly finished with this. So 50 times by minus 2 plus 50 times by 9.8. So we get the reaction force of this one is equal to 390 newtons. And there we go. So let's just have a check of that. Brilliant. 6 marks in total there. You can see where those marks are broke down. So next up, you're going to have a go at some questions yourself. Have a go at all of these questions. Make sure you can understand them. These are tricky questions. People struggle with connected particles. So make sure you have a go at all of them. Make sure you get them right. Remember that maths is about doing questions. It's about doing maths rather than just watching a video. Okay, that's really important. Thanks very much for watching, and I'll speak to you soon.